Hello, good morning everyone. My name is Satria Permana Siwi, and today I'll be presenting our work on building a question answering system on top of Enriched knowledge graph for Indonesian geographic information. This is joint work with my supervisor, Mr. Kemas Wiharja, and my colleagues Raihan Atsal Hafizh from the School of Computing at Telkom University in Bandung. Over the next 12 minutes, I'd like to show you how we transform a grade 11 geography textbooks plus external source like Wikidata and Wikipedia into a working bilingual question answering system that outperforms a large language model baseline while making zero factual hallucination at the retrieval layer. So here's how I will structure the talk. I'll begin with the motivation. Why this problem matters for Indonesian education. Then I will walk through the four research gaps we identify and the contribution we make. The bulk of the talk covers our four-phase methodology followed by experimental results against three baseline, and I will close with an honest discussion of limitation and feature works. So let's begin. The first one, imagine you are a grade 11 student in Indonesian studying geography. Your curriculum covers over 17,000 islands, 34 provinces, dozens of mountains, rivers, and administrative structures. But the information you needed is scattered across government textbook, Wikipedia articles, administrative databases, and news platforms. To answer even a moderately complex question, say, which province contain active volcanoes above the 3,000 meters? A student has to manually search several sources, synthesize fragmented facts, and reconcile contradictions. It's slow, and it produces incomplete understanding. Knowledge graph are a natural fit here. They represent information as interconnected entities and relationships, but applying them to Indonesian geography is genuinely hard for four reasons. On the right side of the slide, the first is the archipelago itself has complex spatial structure. The second, entity naming appear in both of Indonesian and English. Gunung Semeru and Mount Semeru refer to the same mountain. The third, structural data for Indonesian entities is limited compared to Western resources. And the fourth, textbooks contain implicit knowledge that requires inference, not just literal extraction. So, our approach is shown in the blue box at the bottom is to build an enriched knowledge graph from authoritative textbook content, validate with the external sources, and expose it through bilingual semantic search. Okay, when we review the literature, we found four consistent gaps. The first gap is existing system for systematic textbook and extraction rarely archive coverage above 95%. The second gap, multi-source enrichment frameworks like validation strategies that maintain acceptance rates above 90%. Validity tends to degrade as you scale. The third gap is the question answering system predominantly served in English queries. Bilingual Indonesian English evaluation is underexplored. And the last gap is about the choice between the entity-centric and relation-centric enrichment is usually made without theoretical justification. Our work addresses all four gaps through the integrated four-phase framework I will describe next. Okay, let me start with the highlight results. We extracted 7,849 triple extracted from the textbook, 76.4% growth over the manually annotated baseline of the 4,449 triples. External enrichment added 2,305 validated triples with 96% acceptance rate, meaning our geographic validation actually holds under load. The final when the final system achieves 89.7% semantic accuracy with an average response time of 0.3 seconds. And critically, this is the number we'd like you to remember. We outperform a pure large language model baseline by 13.5 percentage points, while producing zero hallucinated facts at the retrieval layer. Below, you can see four phases: construction from the textbooks, enrichment with external sources, processing and Neo4j build, and finally, the question answering system itself. I will through each one. Okay, the first page is about the knowledge graph construction. Manual extraction is time consuming and inconsistently. So we use a hybrid approach, rule-based pattern rule-based pattern matching combined with fuzzy entity matching. On the left, our fuzzy entity matchers use four strategies to handle name variation: direct substring for exact containment, word-based matching that requires 70% token overlap to handle reordering, compact matching that ignores spacing. So Pulau Papua with spacing and Pulau Papua without spacing as are treated as the same entity. And finally, acronym detection for uppercase abbreviations. On the right, you can see how five extraction rules contribute to the total. The dominant rule is mutual detection, where, where both of the subject and object appear in the same textual context. That accounts for 55% and all extracted triples. High confidence predicates like adalah and terletak di contribute another 23% and high priority geography subject, major island, provinces, and contribute nearly 20%. The result is in the blue bar at the bottom. There are 7,849 triples extracted, with a 76.4% growing over the manually annotated baseline. Okay, let's move to the next slide. On the phase 2, we are talk about knowledge graph enrichment process. On the left, we explain why we adopt an entity-centric enrichment strategy. External sources like Wikipedia, Wikidata, GeoNames, and OpenStreetMap are all entity indexed by the design. They organize data around article titles, Q identifiers, or geographic features IDs, not around relations. So, querying by entity is architecturally aligned with how these sources work. For our 4,558 unique entities, we need roughly 4,558 API calls. A relation-centric approach would have need tens of thousands. On the right side, we have the validation gate. Each candidate triples gets a confidence score with multiplicative penalties times 0.8 if the predicate is not geographic, times 0.6 if it falls outside Indonesian context, and times 0.5 is for invalid data quality. We accept only triples with score above or equals to 0.6. The bars at the bottom show that what actually worked. Wikipedia Indonesian contribute 1,420 triples and 25% success rate. And Wikidata added 984 triples at 17%. GeoNames and OpenStreetMap, despite of our best efforts, return zero usable triples due to authentication issues, name mismatch, and read limits. Total, 2,305 validated triples in 96% acceptance. So let's move about the phase 3, about the pre-processing and Neo4j construction. The tree cleaning operation shown on the top lowercase version unifies capitalization variants Pulau Papua with the lower cases, and Pulau Papua with the caps lock. all become the same key. Underscore removal handles delimiter-based compound names, and white space normalization eliminates inconsistent spacing. The growth funnel below tells the story visually. We started with the 4,449 baseline automated extraction pushed to that to 7,849 triples. External enrichment broke out to 10,145 54 combined triples and get insensitive to duplication because textbook content repeats across chapters and external sources confirm many textbooks facts, reduce the final graph to 9,289 unique high quality triples. That's the net 49.6% growth over the baseline with quality preserved. The final graph covers all 34 Indonesian provinces across 12 geographic features types. So let's move our phases. The fourth phases is the question answering system itself. The pipeline shown on the top when a user submit a query, say, di mana letak Gunung Merapi, we encode it into a 84 dimensional vector using the Fairface multilingual mini LM L12V2 sentence transformer. Every triple in the graph is embedded into the same space by concatenating subject, predicate, object as text. We then compute constant similarity between the query and every triple embedding, keeping only those scoring above or equals to 0.3. Finally, we rank by similarity. The formula for constant similarity is shown in the bottom left card because query and triples share the same 384 dimensional space. We get cross-lingual matching for free. An English query about Mount Merapi can retrieve Indonesian triples about Gunung Merapi. On the right, we support two answer generation modes, template mode produce deterministic traceable answers in about 20 milliseconds. LLM enhanced mode uses Grok Llama 3.370 billion model to synthesize an average of 8.7 retrieved facts into a natural language paragraph. Crucially, the LLM only sees validated triples, so the retrieval layer itself introduces zero hallucination by design. Okay, this part I will talk about the experimental setup. Our dataset is the official grade 11 geography textbooks by Budi Handoyo, published by Kemdikbudristek in 2022, all about the 189 pages across 4 chapters with 4,449 manually annotated baseline triples. You can see the per chapter distribution in the 4 cards. Our evaluation protocol shown at the bottom left uses 50 queries across 5 categories: location-based, attribute, relationship, comparative, and comprehensive. So every query was posed in both Indonesian and English to test bilingually capability. 2 annotators independently judge correctness, and we archive a coherence kappa of 0.89, indicating substantial agreement. We acknowledge that 50 queries is a modest sample size. I will return to this in the limitations. On the bottom right, our 3 baselines, a pure LLM with no graph access, classical keyword with TF-IDF, and a textbook-only knowledge graph, and an ablation that tests whether external enrichment actually matters. McNemar's test confirms our improvement are statistically significant at p less than 0.01. Okay, let's look at let's look at the construction result. The top chart, uh, per chapter, growth, bab 3 or bab 3, cultural diversity showed the highest growth at 126%. Was thinnest there, and there were many implicit cultural geographic relationships to discover. Bab 1 or bab 1 on geographic position also more than doubled. Bab 4 or bab 4 on disaster mitigation grew 40%. This chapter already had strong baseline coverage. The five cards at the bottom summarize the final graph. 9,298 unique triples connecting 4,712 distinct entities through the 143 predicate types. All 34 Indonesian provinces are covered, and Indonesia itself sits as the central hub with 89 outgoing connections, a hub and a spoke topology that suits geography reasoning. Okay, on the QA performance, the table on the left shows the retrieval at different depths. At k equals 1, we achieve 0.92% accuracy. At the top, uh, the top result is correct 9 times out of 10. Accuracy gradually decays as a k increases, which is expected and confirms our semantic ranking is working. Average response time stays under a quarter of a second up to k equals 10. On the right, accuracy by question category. Location-based queries performs at the best 95%. This map directly onto textbook content the curriculum covers well. Attribute queries asking for numbers like population, elevation, and area reach 92%. And this is where external enrichment shines. 71% of the facts used to answer attribute question come from Wikipedia, not the textbook. Wikidata give us the precise measurements the textbooks only discuss in the prose. Comparative queries are our weakest category at 81% because they require the system to synthesize multiple facts, closer to reasoning than retrieval. Okay, the most important slide of the top. Look at the top row of the table. Our enriched knowledge graph carries 89.7% accuracy with 0.23 second response time. And the number I'd like you focus on 0% hallucination rate. Now, look at the second row. Pure RLM baseline using the same Llama 3.370 billion model, but without access to our graph, accuracy drops to 76.2%, and the hallucination rate jumped to 18%. In nearly 1 out of every 5 queries, the LLM confidently generated a plausible but factually incorrect fact, wrong population figures, incorrect elevation, and in some cases, references to geographic features that simply do not exist. Keyword search, third row, collapsed to 58.5%, 0.4%. It's fast, but semantic understanding is essential of varied natural language phrasings. The fourth row, the ablation baseline, a knowledge graph built from textbook without external enrichment. It achieves 1.3% better than the LLM and keyword search, but 80.4 percentage points behind our full system. The gap is entirely attributable to Wikipedia and Wikidata enrichment. The three cards below summarize the story. Plus 13.5 percentage points over pure LLM, plus 80.4 points over textbooks only, and 0 percentage retrieval hallucination. One more finding at the bottom, the largest single gap, the largest single gap was on attribute queries, where our system reaches 92% versus 61% for the textbook only ablation. That's plus 31 percentage directly from Wikidata structure properties for measurements textbook doesn't cover in numeric form. Okay, I want to be honest about what this system cannot yet do. The first one, we built a graph from a single textbook plus Wikipedia and Wikidata. Topics underrepresented in those sources cannot be answered reliable, regardless of search refinement. The second, bilingual handling is inconsistent. Most of the time, the multilingual model aligns English and Indonesian entities well, but occasionally English queries fail when the model cannot reach to the Indonesian entity naming in the graph. The third, our evaluation set of 50 queries is indicative, not conclusive. Context length limits in the embedding model and LLM restricted us from running larger batches in one go. A several hundred query benchmark is planned for future work. And the fourth, knowledge graph store information strictly as subject predicate object triples. This support fact retrieval very well but limit complex operation like superlatives, which is the tallest mountain in West Java. Aggregation and multi-helping reasoning. Okay, to conclude, we deliver end-to-end question answering system for Indonesian geography. 7,849 triple extracted at plus 76.4% crew. 2,305 enriched triples at 89 at 96% acceptance and 9 and 6,298 unique triples in Neo 4G, covering all 34 provinces. The system archived 89.7% semantic accuracy at 0.23 seconds bilingually and outperforms a pure LLM by 13.5 percentage points with zero retrieval hallucination. For future works, there are three priorities on the right. The first one is about the technical extensions, additional input formats, self-hosted language models, and web or mobile interfaces. And the second, classroom deployment, piloting with real students and adding features like adaptive questioning and progress tracking. And the third one, or the last one, is about the extending the methodology to our other subjects, such as history, biology, chemistry, where the textbooks-based question answering could bring similar benefits. I think that's all from me, and thank you.